All right, these are the slides on simple machines. So this whole unit has been about energy. And simple machines basically wraps up energy. So energy is the capacity to do work. Now we also learned about work, right? So if work is done to an object, the energy of the object will change or transform. Now three conditions must be met in order for work to be done. So a force must be applied. That object moves through some displacement, and some component of that force is in line with that displacement. So back to this original question, how do people use everyday items to use work to their advantage? So we did the created energy lab. So in this lab, this was just looking at 20 different common items and dragging them into different categories, labeling the categories. Now all the spaces for the categories don't have to be used. There were 6 different categories, but you could categorize them however you wanted, right? You needed at least 2, right? Then label the categories. So part of this was explaining how the items were categorized. So if you're looking at these, like an example, I'd be like, maybe rigid is one, right? So you have some that have hinges, but some don't. So like I would put crowbar, axe, broom in there. I could also see another category as like a wheel, right? So you've got skateboard as wheels. There's like a bike wheel. There's a wheelbarrow that's got a wheel on it, a gear. So that could be one. It could do like outside versus inside. So there's a lot of different categories that you could come up with. Now, explain what all the items have in common. What do they do? So just they all help us out, right? So like the example would be if somebody just put a piece like a log in front of you and said, "Hey, tear this open with your bare hands," you would not be able to do that. But if someone gave you an axe, you could, right? So like these help you out. Now, do any of the items create energy? Explain why or why not. Well, no. Items do not create energy, right? You cannot create energy. Now, that brings us to this question. What are simple machines? So simple machines only help you do work. They do not help you do more work. You cannot get any more work out of them than you put into them. So the work input does equal the work output. Now that's for an ideal machine. Now there are 6 basic types of simple machines. You have the lever, wheel and axle, pulley, inclined plane, wedge, screw. And a simple machine can do 3 things. Now it's not one of 3 things because they can do more than that if need be. So change the direction of your applied force. They can multiply your force at the expense of distance, and they can multiply your distance at the expense of force. So we've already looked at an inclined plane, and you'll notice that in all of those scenarios, the same amount of work is done. You don't get any more work out of this. You're lifting the same object to the same height. But in that, like what a ramp does or an inclined plane is that it multiplies your force at the expense of distance. So we did the lever lab, right? And in this lab, what we did was we were balancing out a 10 Newton mass, right? And we were balancing it out with 2 newtons and 5 newtons. Now, if you'll notice, you look over there, well, you can see that to balance the 10 Newton mass with 2 newtons, it had to be 50 centimeters away. Now to balance that 10 newtons at 10 centimeters away with the 5 newtons, it only had to be 20 centimeters away. Now, then the next one was taking the meter stick and trying to lift that 1 kilogram or 10 Newton mass off the table while slowly moving your hand toward that mass. And it should get easier and easier as you get closer and closer to that mass. So the question is, what can be said about the values of W out and W in? Explain this phenomenon. Well, they should be about the same. And in this case, they were the same, right? And that's because you cannot create or destroy energy. You cannot get any more work out of a machine than you put into the machine. So what happens to the effort needed to balance the load the farther the effort was to the fulcrum? Use the data to justify your answer. So notice that at 20 centimeters to balance out those 10 newtons at 10 centimeters, it only had to be 20 centimeters away. Now at 50 centimeters, it was 2 newtons. So the farther you get away from the fulcrum, the less and less force that needs to apply. It's just farther away from that fulcrum. So explain how a lever affects the relationships between the magnitudes of the effort and load to the distance those forces are to the fulcrum. So this is kind of the same question, but just a little more layman's terms. Essentially what it's saying is that the farther you get away from the fulcrum, the less force that you have to provide to lift that load. But you're going to have to apply that force for a longer distance. So we did look at a lever. Now a lever is a simple machine consisting of a beam or rigid rod pivoted at a fixed hinge or fulcrum. Now there are 3 types of levers, and they depend on the location of the effort, load, and fulcrum. So we have a first-class lever. The fulcrum is in the middle of the effort and the load. Second-class lever, the load is in the middle between the fulcrum and the effort. So the first-class lever, that's like, like a crowbar, or the lever in the lever lab, or like a hammer when you're trying to pry it, or tweezers down there. Scissors is a good example as well. Now, a second-class lever, the load is in the middle between the fulcrum and the effort. That's like a wheelbarrow. And a third-class lever, the effort is in the middle between the fulcrum and the load. Now, that's like a lot of muscles in your body, a lot of the joints in your muscles are a third-class lever. And like another example is like a broom or a hockey stick. Now, what a third-class lever does is you're multiplying distance at the expense of force. So like think about a broom. You're barely moving your hand as you're sweeping, but the end of that broom is moving a lot. You're just not as strong. You won't be able to lift as large of a force. Same thing with your hand. You're getting a lot of distance, but you're not as strong as your bicep. Your bicep's just going to contract just a little bit, moving your arm a lot of farther distance. So what is the law of simple machines? So the law of simple machines simply states that the work that you get out of a machine is simply the work you put into the machine. Now, for an ideal machine, the work output exactly equals the work input. In other words, you cannot get something for nothing. So now let's look at mechanical advantage. So in order to lift a heavy object up a given distance, you apply a smaller force but through a longer distance. So mechanical advantage is the ratio of input distance to output distance. It basically tells you how much a machine will multiply your force. So let's take a look at a problem. So an object with a weight of 60 newtons is pushed up an ideal inclined plane. So that means no friction for a displacement of 5 meters to a height of 2 meters. What force was applied to the object in pushing up the inclined plane? How much work was done to the object and lifting it to that height? And what is the mechanical advantage of the simple machine? So we're looking for that input force, right? We know the output force, right? We know the distance out. We know the input distance, right? We know we're just lifting a 60 Newton object straight up straight up 2 meters, right? That's how much work is done, right? Now, so all I do is I plug it in my law of simple machines, right? So 60 times 2, that's 120. That's the amount of work that this machine does by lifting it up to that height. And I get the input force is 24 newtons. So to lift uh, a 60 Newton object up 2 meters, I only had to apply 24 newtons. However, I did have to apply it for a longer distance. Now I can calculate the mechanical advantage. Well, I take the input distance, which pushing it up 5, divided by the height, which is 2.5. That's basically how much this machine is multiplying my force. Well, now let's look at efficiency. Now, in real life, we encounter friction. Real machines must overcome energy losses due to friction. So for a real machine, the workout does not necessarily equal the work input. In fact, no machine is 100% efficient in real life, right? That's always going to be true. So let's take a look at that exact same example. So an object with the weight of 60 newtons is pushed up a real inclined plane. So that means there is friction with a force of 30 newtons for a displacement of 5 meters to a height of 2 meters. How much work was done to the object by pushing it up the real inclined plane? Ideally, how much work should have been done to raise the object? So that's basically the gravitational potential energy, right? 60 newtons straight up, 2 meters, that has gravitational potential energy, no losses. But there is going to be losses to the environment due to friction, heat, sound. So what is the mechanical advantage of the simple machine? What is the efficiency of this real simple machine? So I know everything, right? I know those before. I know output, distance, and force, input, distance, and force. But now I can calculate that mechanical advantage. Now notice, mechanical advantage doesn't have anything to do with the forces, right? It has to do with those distance. So ideally, this machine would multiply my force by 2.5, right? And there's another concept, ideal mechanical advantage, real mechanical advantage, but we're not going to get into that. Just the mechanical advantage doesn't change with the efficiency in this one. All right, so now we can calculate the efficiency, right? So we look at that and we know that the work output is basically, that's it, right? So that's the gravitational potential energy, 60 times 2, which is 120. But notice that if you multiply the work, the input work, which was 30 times 5, that's going to be 150 joules. So of the 150 joules that was put in, 120 went into lifting the object. The rest was dissipated as heat, as sound, like friction was causing that. So now I can calculate the efficiency. It's 80%. 80% of the energy of that work put into this machine went to lifting it. The rest was dissipated. So now let's answer this one, though. Is having a simple machine with a low efficiency necessarily a bad thing? Well, let's take a look at this, right? If a machine is capable of doing some work in the reverse direction after the effort is removed, then the simple machine is known as a reversible machine. Now, this condition for a machine to be reversible is that its efficiency should be more than 50%. So think about like lifting that lever up and letting it go. Well, that lever is going to fall back down like a seesaw or that teeter-totter. Now, a non-reversible machine has an efficiency less than 50%. That means the losses are more than 50%. The machine is self-locking. So just think about a screw. The screw is the most common example of a non-reversible machine, or that self-locking machine, because a screw is basically just an inclined plane. It's just wrapped around that central core. Now, when you put a screw into something, when you remove that drill bit or that screwdriver, it's not going to just reverse itself. It's not going to fall out. In fact, you don't want that to happen. You want the screw to have a very low efficiency. Look at a car jack. Well, you're still going to get a mechanical advantage. You're lifting a giant vehicle by applying a smaller force for a much longer period of time. But when you release the jack, when you remove that effort, you don't want it to reverse. You want it to self-lock. You want some of these objects to have a low efficiency. Like an inclined plane can also be, if like you let it go and it doesn't come back, the friction can it can be less than 50%. That might be something that somebody wants. A wedge driven into like a block of wood, like an axe, it's not going to reverse itself if you remove the effort. So these are all examples of like machines that have an efficiency less than 50% that could be designed, especially for like a screw or a car jack. So we ended with the pulley simulation. So if we look at the pulley simulation, 100 newtons was applied to all of the machines, or all of this, right? Now notice that the output force and the output work could be calculated. Now, simple machines are able to do three things: change the direction of the applied force, multiply the applied force at the expense of distance, multiply the distance at the expense of an applied force. Which of those can a pulley do? Use the data to justify your answer. So if we're looking at this, we can see that the pulley, if I put in 100 newtons, well, in most of the cases, the mechanical advantage is greater. So it's going to multiply that force at the expense of distance. However, a pulley does something else, though. If you'll notice in all those pictures, a pulley is able to change the direction of that force. In all those examples, that input force is being pulled down, but the object moves up. So a pulley can do those two different things. Now, as the mechanical advantage increases, what happens to the force required to lift the load? Well, we put the input force as 100, but if you go back and do that simulation, what happens is it lowers it, right? It lowers it. You're basically multiplying your force, right? So it takes less of a force to lift that same object. Now, you're just going to have to apply that force for a longer distance. Now, the work done is still going to be the same, right? If you notice in all those examples, the work in is the work out. The work is going to be the same, right? So would the mechanical advantage of each pulley change if each pulley was lifting 100 Newton weight instead of the 50 Newton weight? Explain your answer. Well, no, it's not going to, because if you look at mechanical advantage, it doesn't depend on the input force or what's being lifted. It's just the input distance divided by the output distance. So the efficiency of real simple machines will always be less than 100%. Explain why the efficiency of a pulley is less than 100%. Well, that's because as you're pulling, you can hear like some of that goes to friction in the axles. Some of it gets turned into heat. Some of it gets turned into sound. So you're losing some of that input energy, right? It's not going to be 100% efficient. So if we look at the picture of each pulley and its mechanical advantage, what is the shortcut to find the mechanical advantage of each pulley? Well, if we look at that first pulley, it has a mechanical advantage of 1. Right? There's only one string connected to that weight. Let's look at the next one. Mechanical advantage of 2. Well, now there's 2 strings supporting that mass. Let's take a look at the third one. Well, it's a mechanical advantage of 4. There's 4 strings connected to it. And the last one is a mechanical advantage of 6, and there are 6 strings attached to that load. Now, so it's easy. Just count up the number of strings supporting that load. That's going to be the mechanical advantage. So once again, there is too much unknown in the universe to take a break from learning. Get out there and question everything.